Coming back, so I think all of you can see the whiteboard, right?
Yes, sir.
Okay. So let me just try to explain that question that arised earlier about port forwarding with an example. Say you have a machine which has an IP address, a private IP address as say 10.2.2.3. Okay, and in that particular machine at say port 8080, you are running a web server. Now whenever you are running a web server at this particular port, as you know that this is a private IP address, the outside machines will not be able to connect it. So what we typically do that I have assumed that another machine, and that particular machine has a public IP address, say 202.141.81.2. Well, and that particular public IP address is already available with this machine. That may be any machines in your network. Well, it is not necessarily that these particular machines need to be gateway or need to be the NAT server. It may be the NAT server, may not. Now, what you do, because this is a public IP address, that's why anyone from outside will be able to access it. Now, when people are accessing it, what you do, you take a designated port in this machine, say the port address is 3112, and you say that, well, if any packet is received in this machine for the port 3112, you put a port forwarding rule, and that forwarding rule says that you forward this packet to the machine 10.2.2.3 with port number 8080. Well, and what you do that in your DNS, DNS is sondipc dot iitkgp dot ac dot in, and in that particular machine, you map it with the IP address 202.141.812 with port number 3112. So that means although your web server is not actually running on the machine 202.141.821.2 at port 3112, it is running to another machine, say 10.2.2.3 at port number 8080. And remember that for port forwarding rule, this may not be a private IP address. Even you can do it that, well, you are running it one machine and you do not want people to directly connect to that machine. You want them to connect to another machine, and via them it should come to the machine where the actual server is run. Well, so that you can do, and that way the whenever the request is coming here at port number 3112, you forward it to the corresponding destination, final destination. Now here the difference with the NAT is that in case of NAT, what we have seen that this IP port pair, the public IP and the port pair, is assigned dynamically by the NAT server. But here in this case, they are not assigned dynamically, that they are the static IP address and the port number. Okay, so that is the kind of concept for your port forwarding, and the way it is different from the NAT server.
Sir, one small doubt here.
Yeah.
The default port for the HTTP port is 8080 and 80, right?
Right.
So even if someone is trying to access this website through this 202.14.81.2, the public PC with public IP, then also they'll send the request to the same port on that public PC, right?
Right.
So this 3122 port will never receive a web request.
Yeah, let me try to explain it to you. That a default port address is typically, so for example, a web server. So if you are configuring a Tomcat web server or a Apache HTTP web server, right? So the default port number means if you do not make any change in the config file of that particular web server that you are running, by default it will take port 80 and port 80 or port 8080 as its port number. But there is no hard rule that a web server needs to be run at port 80 or port 88. Even in a Tomcat web server or a Apache HTTP web server, whenever you are running, you can change the apache.conf file, its configuration file, and mention that, well, my web server is going to run in a port 8181. And many of the time we do that because for a security reason, because the automated port scanner and that kind of things, they always try to scan whether port 80 or port 88 is open in some machine. Well, if it is open, then it tries to launch some kind of security attack. So the attacker are always doing that, the port scanner, using the port scanner to scan those ports. So that is the reason many of the web services, they do not want to run them in the default ports of 80 and 88. Well, and that is a scope for configuring them. And in DNS, again, it is providing you the IP address, but whenever you are accessing a website, you can access. So if it is, if you are not in your URL, if you are not mentioning the port number, it will try to connect to the default port. For example, if I am just providing the URL as http://sondipsi.iitkgp.ac.in, then it is going to connect to port 80 or port 88. But if you are providing the URL as http://sondipsi.iitkgp.ac.in:3112, then it understand that, well, the web server is particularly running in the port 3112, and it is then going to connect to the port 3112 instead of the default port.
Yes, sir. So the one who is accessing this should know on which port it is running, right? On this
they need to know in which port it is running.
Ah, okay. Yeah. So that is what I.
Correct.
Okay. Thank you.
Okay. Let us go back to our original slides. So let us start discussing about the ARP or the Address Resolution Protocol, which is again a kind of very important protocol for the IP services that basically provides support for actually forwarding the data in the internet. Okay. Now, what we have seen that the routing is typically done based on the IP addresses by making a lookup in the routing table. Well, and that way we basically decides that what is going to be my next hop in the layer 3 of the protocol stack, in the routing layer. Now assume that, well, you are sending a packet for the IP address, say 202.141.821.78, and the routing, so at every hop you are looking into the routing table, and at every hop it has forwarded the packet, and finally it has forwarded to the gateway of the original machine. Say the gateway is 202.141.81.0, that is the corresponding network, and you have received the packet in the gateway. Well, now whenever you have received the packet in the gateway, then the question comes that how you are going to forward the packet from the gateway to the final destination. Okay, so that is my challenge here, because the gateway machine and the final destination might have multiple different layer 2 switches to which they are connected. Well, because I think I have mentioned that earlier, that in a typical network connectivity, we interconnect the machines with the routers via multiple different layer 2 switches, particularly because the routers are very much costly. So in the router architecture in yesterday's class, we have seen that a router contains the specialized hardware like a TCAM, and because of the TCAM hardware, whenever you are forwarding the packet, it actually makes it much more complicated, and it actually makes it the system much more costly. So that's why what typically happens, or the way such kind of system typically works, is that you forward, so you interconnect your machine with the gateway via multiple different layer 2 switches. Okay, and so a typical architecture is that all the machines which are there in our software lab, they are connected to a layer 2 switch, and then that switch is connected to another switch, and finally that switch is connected to the layer 3 router, which is the gateway. So that is the kind of typical architecture. Now, in this case, what you see that, well, the gateway machine that is not directly connected with your final destination. So it is not, there is not a direct physical link between these two machines. Rather, there are multiple different layer 2 switches in between. So the question comes that how you are going to forward the packet from this particular machine's particular layer 2 particular router to the final destination via these different layer 2 switches. Okay. Okay. So the procedure is something like this, that and this kind of things actually can happen for or true for every layer 3 hop in the internet, right? So even for the intermediate hops, the two intermediate hops, layer 3 hops, may not be directly connected. There might be always multiple other layer 2 switches to which they are connected. Okay. So just me give a minute. I'm having some difficulty in sharing the slides directly. So let me just try to share the slides again. Just give me a minute. Okay, so can you see the slides? Can any one of you please let me know?
Yes, sir.
Okay. So, okay. Yeah. So, such kind of scenario can happen in any intermediate node in the network. Well, so the question comes that how I am going to forward the packets, or how I can find out that what is the next hop in layer 2. Because see here, if I want to forward the packet between these two different routers, I need to forward it via this layer 2 switches, right? And the layer 2 switches also contains a kind of mesh topology among themselves, and that way, whenever I am forwarding a packet, I need to forward it from one layer 3 hop to the next layer 2 hop, and from that next layer 2 hop to further. Well, so the question comes that how will the router know the MAC address of the next hop device? Because in layer 2, if I want to forward a packet, I need these MAC addresses. Well, so that is the kind of challenges that we have, and for finding out the MAC addresses of the layer 2 devices, actually what I need to do, I need to find out the MAC address of the final destination. Well, so typically what happens that in such cases, that say from the layer 3 forwarding, you move to the layer 2 forwarding. In layer 2 forwarding, you create a kind of spanning tree across the switches. So the detailed procedure of constructing this spanning tree across the switches, that we will talk later on. But ideally, you create a spanning tree of that switches, and then you use the MAC address to forward the packet. Okay, so broadly it happens in this way. Well, say for example, this is a kind of end-to-end network. Well, assume that for every layer 3 devices, I have an IP address and the corresponding MAC address. The IP address I have written here, and the MAC address is written as MAC S1, MAC R1, MAC R2, MAC D1. Now, for the first packet which is being originated, for that the source IP is 202.141.81.2. The source MAC is MAC of S1. The destination IP is 13.187.34.79. That is the final destination, and I need to find out what is going to be the destination MAC. Okay, so can any one of you by any chance tell me that what should be the destination MAC here? Any idea? So out of this MAC S1, MAC R1, MAC R2, MAC D1, what is going to be the destination?
MAC D1.
MAC D1. Okay. Any other answer?
MAC R1.
MAC R1. Okay. So I think all of you are actually grouped between these two answers, MAC R1 and MAC D1. See, from a layer 3 hop, whenever I am going to forward the packet, I need to forward it to the next hop. Well, next layer 3 hop. And how I will get the next layer 3 hop? I will get the next layer 3 hop from the routing table lookup, right? So the routing table is saying me that you need to forward the packet to 202.141.210.3, right? And this information that I now need to forward the packet to the next hop 202.141.210.3, that should be somewhere in my packet headers. Well, and where it will be. See, the final destination MAC I do not need, because I can do a forwarding using MAC only when within a subnet. Well, so when it is in a completely different subnet, I cannot do this MAC-based forwarding. Well, the detailed mechanism for MAC-based forwarding we'll be talking in the subsequent classes, maybe in the next class. But the broad idea is that I cannot do MAC-based forwarding among multiple subnets. I can only do it within this subnet. So that means only within the subnet in between 202.141.81.2 and 202.141.210.3, I can do the MAC-based forwarding. Well, now the routing algorithm tells me that your next hop is going to be 202.141.210.3. What I actually need, I need to find out the MAC address of 202.141.210.3. So the IP address that is being returned by the route lookup, and put up the corresponding MAC in my destination MAC. Okay, so that means so the routing table, either through the default gateway or the route lookup, it tells me that the next hop is going to be 202.141.210.3. Well, So once you get, you need to find out the MAC of that. So the question comes that how do the network know that what is going to be the MAC address? Okay, and as I was mentioning earlier, that the network need to do a layer 2 forwarding here. That means forwarding based on the MAC address. So typically what we do, that we use a protocol called spanning tree protocol that runs at the data link layer, not at the IP layer. So the detailed methodology of the spanning tree protocol we'll discuss later on whenever we'll discuss about the layer 2. So what you do, that you create a layer 2 tree from the source to all other nodes. Okay, so that means from 202.141.81.2, I will create a spanning tree within that subnet. So that will eventually reach to 202.141.210.3, right? Now, once that is available, then what we typically do in L2 forward, that the MAC frame is broadcast to all the L2 devices in the subnet using this spanning tree. Okay. So in case of layer 3 routing, we use that specific routing. We find out that, well, this is going to be my logical next hop, logical next layer 3 hop. But in layer 2, we do not have any such kind of routing mechanism, because here actually I need to physically deliver the packet. Now to physically deliver the packet, we use this concept of broadcast in layer 2 subnet. That means whenever I have a spanning tree, I broadcast the packet across that spanning tree. And here you can just imagine that why we use a spanning tree to broadcast, just to prevent the routing loop. If we do not use a spanning tree and blindly broadcast the packet, then there are multiple different loops here in the diagram. And because of those loops, it will happen that the packet will not get forwarded, rather it will get looped within that particular forwarding loop. Okay. Now to avoid such kind of forwarding loop, we use the spanning tree kind of architecture, so that routing loop is avoided. Well, now over that spanning tree, I broadcast the packet. Now broadcast means every layer 2 devices in that subnet will receive that packet, and that happens in our Ethernet network. Actually, within your subnet, you actually receive all the packet for all the different machines. So whenever we'll discuss about the data link layer, I will explain that to you in details with an example. But anyway, for the time being, just take it up that through that broadcast, once the device receives a frame, it extracts the destination MAC address and matches it with its own MAC address. Well, and if there is a match, it accepts the frame, forwards it to the upper layer. Otherwise, it drops the frame. That means whenever I have broadcast this MAC packet with the MAC address of 202.141.210.3, eventually the machine which has the IP address 202.141.210.3 and MAC of R1, it will receive the packet. It will match the destination MAC with its own MAC. Well, and it will see whether the MAC address has a match or not. If the MAC address matches, that means this packet is destined for me. So I accept that packet and send it to the upper layer for the further processing. If there is not a match, then I will drop the packet. So that way the intermediate layer 2 switches, they will drop the packet, and only the final hop which is intended to get the packet, it will receive the packet. Okay. So that's why we need the destination MAC address in this kind of frame. Now the question comes, how does a device find out the MAC address of the next hop LTP device? So from 202.141.81.2, how will I find out that what is the MAC address of 202.141.210.3, which is the MAC of R1? Well, so for that we use the protocol at the layer 3, which is called the Address Resolution Protocol, or ARP. Okay. Now we'll see the details of ARP in a while, but using ARP, I find out the MAC address, put it in the packet. Well, then I use spanning tree protocol to forward the frame to R1. Now once R1 receives it, R1 repeats the same thing again. Well, so what R1 does, R1 again receives the packet, it moves to the IP layer, and then the IP layer will check the destination IP, that the destination IP is 13.187.34.79. It will make a route lookup, find out that what is going to be the next hop. Okay. So the next hop is going to be 223.191.21.45. Well, so it will actually update the source MAC and the destination MAC accordingly. So for the destination MAC, it will make a route again ARP lookup. By ARP lookup, it will find out that what is going to be the MAC address of the next hop information that is written by the router, that is 223.191.21.45, and it will put up that information at the destination MAC. Okay, and also the source MAC will get updated. I forgot to change the source MAC. The source MAC will be changed to MAC of R1. Okay, the source MAC here will be changed to MAC of R1. Now, once the source MAC is getting changed to MAC of R1 and the destination MAC is changed to MAC of R2, then you forward the packet further. So it will use the spanning tree protocol the same way, and it will reach to that machine suite 223.191.21.45. Again, it will do the same thing. It will try to make a search for the destination MAC, try to find out that what is going to be the destination MAC. And it is in the same subnet, it will use the ARP protocol to find it out and find out that the MAC is going to be the MAC of D1. So it will update the destination MAC as MAC of D1 and the source MAC as MAC of R2. Okay, remember that I forgot to update the source MAC in these slides. So the source MAC will get changed at every hop as well. So the source MAC here will get changed to MAC of R2. And again, it will use the spanning tree protocol to forward it to the final destination. Right? So that is the way a packet is actually being forwarded in a network by taking the help of the IP address, the next hop information which is being forwarded or which is being sent by the routing table, and then finding out the MAC address of that next hop using the address resolution protocol. Well, now let us look into this address resolution protocol. So this ARP protocol actually uses two different type of messages. So one is the ARP request and another one is the ARP reply. So this ARP request and the ARP reply contains the four different addresses primarily. The source hardware address, that means the MAC address of the source. The source protocol address, that means the IP address of the source. The target hardware address, that means the MAC address of the destination. The target protocol address, that is the IP address of the destination. Now this ARP request message, the ARP request is a broadcast in the network with the broadcast IP address and the broadcast MAC address. So 255.255.255.255 is the broadcast IP address and the corresponding broadcast MAC address is FFFFFFF. So for the broadcast IP address, it is not necessary that you use 255.255.255, rather you can also use the broadcast IP address of your subnet. Okay, and once the device receives an ARP request message, so ARP request need to be broadcast because I know the IP address, but I do not know that in which particular machine has that IP address. So that's why I need to broadcast it, so that everyone in the subnet receives it. So once everyone in the subnet receives it, they check that whether they have the target protocol address. If they have the target protocol address, they reply back with the target hardware address. So here is an example. Okay, so this particular packet, I want to find out the IP address of 202.141.86.22. So I construct the ARP packet like this. So the source hardware address is MAC of R1. The source protocol address is 202.141.81.2. The target hardware address, I need to find it out. And the target protocol address is 202.141.86.22. Now I broadcast that packet. To broadcast that packet in the packet header, IP header, my source IP is 202.141.81.2. The destination IP is 255.255.255.255. The source MAC is MAC of R1. And the destination MAC is again the broadcast. Now I broadcast that packet and the packet eventually receives to both the machines. Okay. And every machine will check whether they have the target protocol address. And here, this first router MAC of R2, it sees that the target protocol address matches with its address. Okay. And that way it will process this ARP request. The other machine, other router will drop the ARP request because the target protocol address does not match with its own IP address. Now this particular machine, it will construct the ARP reply. In the ARP reply as a target hardware address, it will put up its own hardware address and then unicast this ARP reply to the machine which has actually requested for the MAC address. So here the source IP will be 202.141.86.2, but the destination IP would be 202.141.81.2. The source MAC will be MAC of R2 and the destination MAC will be MAC of R1. Okay, so that way this ARP reply will be sent to the machine who had requested for the ARP packet, and it will then get to know the MAC address corresponds to 202.141.86.20. So this is typically the protocol based on which the ARP forwarding occurs. We use this ARP to find out the hardware address or the MAC address for a particular IP address and use that information to forward the packet using the spanning tree protocol. Okay, so that's all about ARP. Let me know if you have any doubt in ARP. Any doubt or any query? The exact spanning tree protocol, how it works, the details we will be talking while we will discuss about MAC starting from the next class. Okay. So I'm assuming this concept of ARP is clear to all of you. Well, so now let us quickly look into the last protocol in this group of protocols, that is the Internet Control Messaging Protocol or ICMP. Now this ICMP is a part of IP. It is a set of messaging protocol for internet management, error messaging, and network configuration verification. Say for example, the ping, trace route, all these different services that you use that typically uses ICMP. So it provides a feedback when an IP message is sent. So for example, it informs the source when an IP packet is dropped from an intermediate layer 3 device. It checks whether a L3 host is reachable. It can redirect the message. It can make the router advertisement. Okay. So for example, in case of the routing information protocol or OSPF, we have seen that it makes the routing advertisement. So that routing advertisement can be done using ICMP. So that way the ICMP is basically a set of messaging protocols for monitoring or for controlling the network control behavior from the IP layer. Okay. Now it works with IP on top of IP. So for IPv4, we have ICMP version 4. For IPv6, we have ICMP version 6. Now, ICMP messages are typically divided into two classes. So one is the error messages and another is the information or query messages. We'll see an example of both. So the error messages are used to provide feedback to a source, that is a layer 3 device, about an error that has occurred. So for example, if the destination is unreachable, say you want to forward a packet and in a router you are not been able to find out the next hop. Well, or you see that the next hop information that the router is returning, that next hop is not switched on. You cannot reach to that next hop. So if you cannot do that, if you cannot find out the path towards the destination, then ICMP sends a destination unreachable message to the machine which had originated the packet. So that way, the originator or the initial source knows that, well, the destination is unreachable. For example, the earlier kind of diagram that I was mentioning. So in this diagram, say if this 223.191.21.45 is down for some time, well, and 202.141.210.3 is trying to find out the next hop and it is not been able to do so. If it is not been able to do so, then it will send the originator, that means 202.141.81.2, saying an ICMP destination unreachable message will say that, well, the destination that you are targeting for it is unreachable. So that is the kind of purpose for the ICMP error messages. The second type of messages which are there, it is called the information or the query message. It is used by the layer 3 devices to exchange certain information implement certain IP related features and perform tests. So for example, ICMP echo request and echo reply. So if you are sending an ICMP echo request to any IP device, it will send an ICMP echo reply. Okay, we'll see an example of ICMP echo request and echo reply. So this echo request and echo reply, one of the prominent use case of that is the ping application. So I guess that all of you have used that ping application to ping a device. So whenever you are pinging some IP address with the ping application, you see that it keeps on sending the response messages. And if you look into the response messages carefully, you see that it contains the field like ICMP sequence. That is basically the sequence number of the ICMP packet. Now from that echo request and the echo reply, it calculates the time, the round trip time, and it is basically returned. Right. So let us see that how it works, that the ping in case using ICMP echo request and the ICMP echo reply. So the ping application, it generates an ICMP echo request towards the target L3 device. Once the target L3 device receives the echo request, it replies back with an echo reply. And whenever you are sending the echo request, you take a timestamp, say it is T1. Whenever you have received the echo reply, you take the timestamp, that is T2, and you calculate the RTT as T2 minus T1. And that time is actually shown in case of your ping application, that how much time it is taking for sending the packet. So that way the time is being estimated using the ICMP echo request and the ICMP echo reply messages. Okay. So here is another example of ICMP where we use the ICMP error message. It's the traceroute application. Okay. So the traceroute application, it is used to find out the intermediate layer 3 devices or the intermediate hops between a source and a final destination. So if you do a traceroute to a particular IP address, you will see that it will show you what is the first hop, what is the second hop, what is the third hop, and so on. Well, so let us see how traceroute works. Well, so traceroute works using two ICMP messages. One is ICMP time exceeded and ICMP destination unreachable. So what is that? So say for example, the source does a traceroute. So to do a traceroute generates a UDP packet. So you set the protocol as UDP, set your destination as D with a particular port, random port. Typically a random port is taken, and you set the TTL field of that packet as 1. What is the TTL field? The TTL field basically says that, well, it is the time to leave. That means that every hop, the TTL field is decremented, and if the TTL reaches to 0, it will drop the packet and send an ICMP destination unreachable message. Okay. So that way, whenever you are sending TTL 1, that means after the packet will be sent to the first hop towards the destination, TTL will become 0 and the packet will be dropped from there, and you will send a destination unreachable message. So that way, with TTL 1, whenever you are sending it, the packet will reach to R1. Well, and at R1, it will drop the packet, and when it will drop the packet, it will send an ICMP packet with the message time exceeded. Okay. So the time exceeded means the TTL has reached to 0. And when it is sending that ICMP time exceeded message, there it is mentioning its source IP, and that IP is actually, you see, it is your first hop IP. So the same way it keeps on working. So next it will send another UDP packet, but this time it will send the TTL as 2, because it has sent it is a TTL as 2. R1 will decrement the TTL further and forward it. So it will reach to R2. R2 will decrement it. R2 will find out that the TTL becomes 0. So when R2 will find out that the TTL becomes 0, it will again send an ICMP time exceeded message with source at R2. And you know that now R2 is in your second hop. Then to get the third hop, you send an UDP message with TTL equal to 3. So R1 will forward it, R2 will forward it. And when it reaches R3, TTL will become 1. And TTL, R3 will decrement it, TTL will become 0. And when TTL will become 0, then it will send an ICMP time exceeded message with source and R3 as R3, and you know that, well, my third hop is at R3. Now you put TTL equal to 4, so it will be reached at D, but whenever it will reach at D, it will see that, well, this particular port is not running any UDP server because you have just sent a random UDP packet, right? You do not know whether a UDP server is running on that particular port or not. Well, so with that particular port, I basically send back again when that will happen. That means no server is running at the port address that is being mentioned. It will send that ICMP destination unreachable message. So that way you know that you have reached to the further hop. So that way basically traceroute works by utilizing the ICMP time exceeded message and the ICMP destination unreachable message. Okay. So that is all about ICMP. So ICMP has various other messages. So if you look into the ICMP specification, you can get the details of those messages. I just mentioned two of the messages which are prominent and used, one in ping application and another one in this traceroute application. So there are other application use cases of ICMP. So you can just look into the you may look into the RFC of ICMP to get to know about all those details. Well, any doubt or any query about all the topics that we have discussed in today's class?
Sir, in traceroute we are using UDP. So what happens if a packet is lost or something?
Packet lost means you will not get a response. So if you look into the this traceroute thing, the output of the traceroute,
Those stars are.
you will see that you are getting the stars. Okay.
Okay.
So the stars means something has happened with that packet. Either the packet got lost, or it might happen that there is a firewall running on that device. Well, it has dropped that packet and it has not accepted it and not sent back any ICMP as well. So it will wait for some time, and if it is not receiving any ICMP within that timeout duration, it will just print the star and go to the next hop by implementing the TTL further.
So one more general doubt, like when we say a packet is lost, what does it actually mean? How does a packet suddenly disappear from the network?
There may be multiple reasons. So one reason is if there is a kind of signaling error. Signaling error in the sense that you are ultimately converting the packet, that is a kind of digital signal to analog signal and transmitting it via wire. Now, if certain signaling error happens within that wire, within your Ethernet cable, might be there is a problem with the voltage and something, and some noise comes. Well, the signal gets distorted and it is not being able to decode that. That is one case when a packet might get lost. In case of wireless, that is too frequent because you are using a wireless channel. It might happen whenever you are sending a signal, another signal interferes with that, and the signal gets distorted, and you are not being able to regenerate the bit stream from the received signal. Another instances is that which are very common, that every intermediate layer 3 devices or even the layer 2 devices, they maintain a buffer. Okay. So for example, a router at every interface, they maintain an interface buffer. And that interface buffer has finite size. Well, now whenever you are keeping on sending the packet, if your buffer gets full, then if your buffer capacity exceeds, then it will not accept any more new packet and that packet will get dropped. Say for example, if you will receive the signal, you decode it at the layer 2, find out the packet, and whenever you are going to put up that packet in the buffer, you see that the buffer is full. If the buffer is full, typically a machine doesn't do anything, it simply drops the packet. So that way the packets typically get lost whenever you are sending it in.
Okay, thank you.
Any other query or any other doubt? Okay, before I close, I have a final question for all of you. Let me see that within the remaining 2 minutes whether you are able to answer it. Why you are using UDP in ICMP? Why not we are using TCP? Can we use TCP here?
TCP will take a lot of time because it needs to verify a lot of things. It needs to make sure that it is delivered and received.
That's partially partially true, but again, there is much more serious concern with TCP. And just think of that, if I want to use TCP like this, what might happen?
Okay, it needs to establish the handshakes and all with each.
Absolutely. So if you send the TCP packet with TTL1, well, so that is going to be the data packet, but your TCP socket or the TCP flow is anyway going to generate the SYN packet, right? For the doing the handshaking. And that SYN packet, it is not make TTL1, it will just keep TTL as a large number. Well, if you can forcefully change the SYN packet and make it TTL equal to 1, that is a different story. But otherwise, you will not be able to do so. You have that handshaking packet. Now, that handshaking packet, whenever you are going to send, you are sending it at a random port. You do not know whether a TCP server or a UDP server is running on that port or not. So whenever you are going to the SYN packet, it is not going to accept the SYN packet. It will simply drop that SYN packet and there will be a SYN timeout. Okay. So that way the expecting behavior that you wanted to see, that means let the packet be forwarded to the first hop and get it dropped from there so that I can get a ICMP time exceeded message, that will not happen with the help of a TCP. Okay, because TCP will not simply send the data packets. TCP will first try to do the handshake. So that is the reason in ICMP we do not use TCP, we use UDP. Okay, good. So let us stop here today. So we'll have the next class on next Tuesday because Monday is the Holi. So happy Holi to all of you. And see you all on Tuesday. Thank you, everyone. Take care. Bye-bye.